Okay? All right, everybody, we're going to get started. This is Dr. Abhishek Savita, who has been working with me since May. He came here from his postdoc in Germany, where he spent the last couple of years working, and you're going to hear about his work there. His work with me, you'll have to hear about another time, like maybe in the spring or next year. Before that, Abhi was in Australia, where he did his PhD at the University of Tasmania, very different from Miami. And before that, he got his undergrad and master's degrees in India at a local university, and then his master's degrees were from the IIT in Karakoram. So Abhi has background both in mathematics and physical oceanography. He spent his time as a postdoc running climate models in Australia. My understanding was he did many of the simulations that went into CMIP6 for the Australian model. So he is responsible for that data, which is a really big responsibility. I'm going to turn it over to him in the spirit of fun, because it's Friday, a couple fun facts about Abhi. So one thing is you might see him often because he commutes either by foot or by scooter on the causeway every day, right? Yes. I see him sometimes when I'm biking by, and even rain and wind, and he's out there. One other fun fact is he just spent some time in India after not having been there for a very long time, and he was able to celebrate a couple really unique holidays with his family. Sister's Day, wasn't it? Yeah. So if you want in the question and answer, you can ask him about his fun times in India recently. So, all right, I'll turn it over to you.
Okay, so good morning, everybody, and thank you very much, Amy, for my introduction, and also Roland for organizing this seminar series and giving me this opportunity. And as Amy mentioned, my name is Abhishek Savita, but feel free to call me Abhi, which is the first four letters from my first name. And as Amy mentioned, I'm going to talk about impact of multidecadal climate mode variability. My title was before the European, but I changed it slightly, and I'll tell you the reason why, the Eurasian climate. And I'm going to focus particularly in the recent decades. I'd also like to, before we start, to thank you, the co-authors who contributed to this work. And as you can see, they are listed here. And Amy mentioned about me, I would also like to add here, I went to India for 1 month, and I promised her I would work from home, but I didn't manage to do that. So there was something also I did an extra there. Okay, so moving forward, Amy mostly mentioned about my academic background and what I did and where. So I'm going to skip this slide. I'll move to another one. So this is the main key or the motivational slide from where the problem starts. So you are seeing in this plot the surface air temperature trend for the time period 1993 to 2030, and this is just particular for the winter season, like the average of December, January, and February. Blue color is showing where the trend is going down, that means its cooling is increasing, and red color is showing where the trend is going up, that is, it is getting more warmer. Additional information, the dots are showing where there is blue and the red are important, that the significant changes. And this is from the observation. So what we found, actually if you look at the Arctic, it's getting warmer and it is significant. This is very well known. We know it is mostly the force. Whereas if you look at this is actually the Europe and this is the Eurasia, and that's even before the title was Europe. I changed it to Eurasia because here we are seeing the significant cooling. And this cooling is not like the first time I noticed it. It is already in for 1 or 2 decades in research community. But there is a big debate about what drives this cooling. There's some papers that suggest it is cooling mostly driven by the change in the sea ice over the Arctic region. There's another some research that suggests, it is mostly because of the Pacific PDO, Pacific Decadal Oscillation. There's some paper that talk about, it is mostly because of the Atlantic Multidecadal Oscillation of the variability. So there's no agreement like what and why. So I looked this further, and by using in the atmospheric model, I'm going to talk about that. But my more intention to understand, okay, how much this cooling is because of the Pacific decadal SST, and how much because of the Atlantic multidecadal or decadal SST change. And the question is why I focus in these two. The reason is that if you look at this is the Atlantic SST and it is positive, but this SST change from decade to decade. In some decades it is positive like this, but another decade maybe go up other way around, become negative. And good example, if you take the average of this and plot the time series which is shown here, so if you see in some years, in some decades positive, here is positive but it is negative. And we call this, or we know this as multidecadal oscillation or multidecadal variability. And the important point here, if you see in the recent decades, I mean the time period, we found cooling here, it is going up. Like the trend is the positive, that means the sea surface temperature over Atlantic is positive. If you look on the left hand side, which is the Pacific Ocean here, with the color we are seeing here, actually it is the typical example of PDO, the Pacific Decadal Oscillation. We also have the oscillation like we have the Atlantic and the Pacific, and this pattern also changed from decade to decade. This is, I mentioned this is the positive, but the other decade it goes around negative, that means this become blue and this become red. And this is the time series which is based on the empirical orthogonal function. So this is, you are seeing the pattern, and this is the index. And you see here, I said it here during the 1993 to 2040, it is going in the opposite direction. That means the condition over the Atlantic and the condition over the Pacific are opposite. So this is how the curiosity comes in mind. Okay, what will happen to this cooling if they are in the opposite patterns or opposite change? Another important thing is that here I plotted the North Atlantic Oscillation. So these two are based on the ocean condition, like how change the ocean surface. And this is the North Atlantic Oscillation, which is based on the sea level pressure difference over the Iceland and Azero. So if you don't know where this location is, I can give you a bit hint. So this is the Atlantic Ocean, and in this map you will see Atlantic here. So this is the sea level pressure difference between, let me find, here and here. And what this, because we computed this based on the sea level pressure anomaly, we call this as atmospheric internal variability. And this is, I haven't applied any filter here, so you are seeing more internal variation. And if you compute the trend, I did, and what we found, the trend from here to here is negative, around minus 2 point something heptapascal in 20 years. So there was a question from the reviewer like, it may be the trend I'm getting may be dominated by the year 2010, because one of the strongest negative years. So what I did, I rechecked this, I removed the year 2010, and then I computed the trend value, and still we found the negative trend, which was significant. So this is the reason I include the NAO to understand, because this is really very important for the Eurasia or European climate as well. Okay, so moving forward, I look at, to understand the impact of this SST anomaly and this one, what I did, we used the open access atmospheric model. So if you are hearing first time, the open access atmospheric model is part of coupled model that is used to generate the European reanalysis product, we known as the ERA 5. Because the reanalysis product is combination like based on both observation and coupled model. And this model was part of that. And what I used the 100 kilometer resolution, and I did the simulation because it's an atmospheric model, so you force with the observed sea surface temperature and the sea ice. And I run the control simulation for the time period 1950 to 2030. Just to add here, I used the similar other radiative and aerosol forcing as used in CMIP6 AMIP simulation. And I did 45 member simulations. And why I did 45 member simulation? Because we are also interested to understand how much the force signal and how much the internal variability. And how we generated the members, ensemble members, we add or change the SST with the range 0.05 minus 0.05 to plus 0.05. That means very tiny changes in the SST. Then we did additional two experiment because in which we removed these patterns. So here is important. I didn't remove just the fixed pattern. What I did, I multiplied this pattern with this time series and then removed from the SST. From the SST I used to do the control simulation. That means I removed the time invariant signature of AMO. And then we call this experiment as no AMB. And then I repeat the methodology for the PDO and we call this experiment is no IPV. So sorry, I'm referring PDO and IPV, but I mean it's both, like internal Pacific variability or Pacific decadal variability. The question is from where I get these patterns. This pattern I did check by using the RFI, but I grabbed this pattern from DCPP CMU6 protocol. And what is DCPP stand for here is the Decadal Climate Prediction Project, which is also part of CMU6, and to understand how the climate change due to these particular patterns. Okay, so let's move to the next one. It's asking me to update something, I'll skip that. So before we move to the key results, I like to emphasize here, we did check the robustness of the open access model, and we published a paper that's led by myself in GMD recently, and in this we checked the mean state biases and also understand how the bias improved if you move from low resolution to high resolution, which is also known in the community, but we check particularly in the open access, and also the time step sensitivity. So time step is not aware of how important it is. Actually, it is important in the model because it does allow you how frequently the fluxes interact with each other. So we check the sensitivity of the time step as well. These are been published by another work led by a PhD student in Louis, who is looking at the impact of the horizontal resolution and the model time step in the extreme precipitation over Europe. And this paper is under discussion. I'm going to submit the reviewer comments today after this talk. So here you are seeing the surface temperature trend. You already seen this in my first slide, and this is from the hat crew. The reason to compare these two to make sure the trend we were seeing before is not data dependent. And we can clearly see in RF5 and hat crew, we do have the strong cooling and it is significant. On the right panel, we are seeing the same like surface temperature trend using the first member. The question why I chose the first member, there was no reason, but first I did the first member, and that's the reason I look at the first member surface temperature trend. So here we can see the trend, the cooling trend is kind of consistent, and the warming trend over the Arctic. But here the patterns are consistent. If you look at the magnitude, like the change at a particular location, they are in models much weaker than what we are seeing in the observation. Another thing, these things we are seeing here in observation or first member is combination of both forced change and also the internal change, like intrinsic variability or of atmospheric side as well as the internal variability of the ocean side.
I mean, can I just
Yes,
ask,
please.
this experiment on the right includes prescribing global sea surface temperatures, and does it include gradient forcing of those
Yes, these are the historical simulation from 1950 to 2014, so include everything, yes.
But we prescribe sea surface temperatures.
Prescribe this observed sea surface and sea ice temperature, yeah.
Okay.
Mm-hmm. So that means observed sea surface temperature and prescribe means we don't have bias from the ocean side. So that's something if you do the atmospheric or image simulation. Okay, so these are the again to understand the change we are seeing. It is because of the forced or unforced. So on the left panel you are seeing the members mean that in the controls, like the 45 member you take the mean and compute the trend, and we are seeing there is no cooling anymore. That means this is the force signal warming the Eurasian region. To understand further, that means in this box mostly the cooling we were seeing before is unforced. To confirm this, I also computed the standard deviation across the 45 members. This is also known in our community as noise. And when you take the ratio of the mean, that is signal, and the standard deviation, which is noise, we'll get the matrix signal to noise ratio. And signal to noise ratio, which is greater than 1, which is shown here in the red color, is forced signal, and if it is less than 1, which is shown here in the blue, is unforced signal. And where you can see very clearly over this region is mostly the change we are seeing mostly unforced. So this is the one of the evidence, like the cooling we are seeing over the Eurasian region is mostly unforced, and one of the key results as well. To verify that if it is unforced, it is oceanic side or atmospheric side, and how much from the Pacific and Atlantic and NAO I mentioned before. So what I did, I take the IPV, MB and NAO index, and then I also take the surface air temperature, which is detrended and signal mean removed. And when I regressed on IPV, which is shown here, and AMB, which is shown in the middle panel, and the right panel is the NAO. What we found, if you regressed on this one, like the NAO, there is strong teleconnection, and it is significant. But if you look at the IPV, we also seen some weaker than the NAO, but still strong teleconnection. But we haven't seen such teleconnection with the AMB. This is the first order check. We haven't just take the index, regressed on the surface temperature, is there any teleconnection or not? So it seems like yes, there is some teleconnection with there is some impact from the IPV and NAO, but there is no impact from the AMB. Just to add here, I haven't filtered the data. This is the NAO more interannual like the NAO. And there's another question I was asked by the reviewer. This is not a right comparison because one you are filtering out the high frequency and another you have. So what I did, I used the NAO in which I smooth out the signal by applying the 11-layer filter, but still we got the same conclusion, but the magnitude a bit weaker than what we are seeing here. So to verify that this is the, as I mentioned, this is the first order check. To verify it further, here we utilize the experiment I mentioned before. So before we discuss that, I like to show the probability density distribution. And here you are seeing the control 45 members trained, and this is the box here I showed here and also mentioned in my previous slide. And you can see, and this black line is the observation, this the solid orange line is the ensemble mean, and this is the dash vertical line, one standard deviation. So first of all, we see here, as I emphasized in my second or third slide, the cooling patterns are captured by the members 1, but not the magnitude. And it is clearly, we can see here, none of the members able to simulate the observed trend we are seeing here is much stronger than what we are seeing in the model. However, half of the model is showing the positive trend, half of the members are showing the positive trends, and half of the other side is showing the negative trends. And if you see, the fit is mostly the normal distributed. When here on the bottom panel, you are seeing the blue is in the control, and we have the additional 2 lines which red refer to the no IPB, and here the orange line is no AMB. And if you see they look kind of similar, but if you give attention on the higher cooling trend values, you see the probability is less than what we are seeing in the control. If you see heat in this area, and also you move to higher trend, like this one. Now it's in IPB, OEM is going up to the control. That means the probability of having larger trend increases compared to the control. Always a bit confusing, so what I did, I used the bootstrapping. I select the 45 members randomly and repeated this for 2000 times, and I got the value like ensemble member mean when you apply the bootstrapping, and this is the significant, like the range, like the confidence, 95% confidence interval. And what I found, if you put this like the mean value plus error bar, the control and no IPV error bars don't overlap to each other. That means they are significantly different. But no control and no MB they overlap to each other. That means they are not significantly different. So this is again confirmed by just looking at this matrix. Like the IPB has some impact over the Eurasian cooling, but not the AMB, which also we seen when we did the first order regression analysis. To further investigate, I used another matrix in which what I did, I computed the difference between the control minus no IPB, which is shown on the top panel, and control minus no AMB, which is in the bottom panel. And what we see here, if you remove the no IPP, here it is cooling trend. That means the cooling we were seeing in the Eurasian region driven by the IPP, and it is significant. Again, it's another way to confirm this. But we are not, and also in the no MB, but it's much weaker. So the two metrics we use, one is the regression analysis and the probability density function. The AMB, we found like AMB had no impact, but when we did the regional differences, we see there is some like very little impact from the AMB as well. So on conclusion, like the take-home message from this work is like the Eurasian cooling is mostly unforced, and it's driven by the NAO. There is some impact from the IPV, but not much from the AMB. So before I wrote like doesn't at all, but by seeing the regional map, there is something. So this doesn't hold like we can say 100% there is no impact. There is something, but very little. That suggests like it is mostly driven by the atmospheric as well as partly by the ocean variability. Although I look at these climate modes, but there is another atmospheric pattern like the PNA, Pacific North American pattern, or we have the Arctic oscillation. So we haven't seen, like, I haven't looked at those impacts in this Eurasian cooling. This is more looking at the decadal scale, but also we have the interannual mode. Like, if you look at the Pacific Ocean, we have the ENSO, which is El Nino Southern Oscillation. If you look at the Atlantic Ocean, we have the Atlantic Nino, or Indian Ocean, we have the Indian Ocean Dipole. So we haven't seen how much this interannual mode, is there any impact from these to this Eurasian cooling, because there's a lot of work is going on in which they talk about the interbasin daily connection. So these are the limitations that can also be done further. Another limitation of this work, I did recheck the contribution of IPP and AMB by doing some sensitive experiment, but we haven't done such experiment by using the NAO. Like, we haven't done experiment. We just conclude based on the regression analysis. That can also be done like by take the NAO and regress on the SST and get the pattern and remove from the control simulation, and then see if we get the same conclusion or not. So with this is what I wanted to say, but I'll stop here and happy to take questions if you have some. Thank you very much for listening and your attention.
Okay. Yeah, wait, John, let's do the questions from the room first.
Okay.
Paquita?
I need a reminder on how the NAO relates to temperatures over Europe. So there's a shift in the jet stream that encourages cooling.
Yeah, because I found like this with the NAO in the negative phase, and the NAO in negative phase like it's changed the jet a bit northward, and that brings a lot of cold air from Arctic to the Eurasia. That's how it has NAO impact on the cooling. So more cold air coming from north to southward.
And that's been observed in the storm tracks that they've shifted.
I really haven't looked at the storm track, but I look at the previous literature, and this is how they explain like the NAO has impact if you have the negative NAO. And I haven't looked at like those things like myself, like looking at how if we have the like regress on the negative NAO on the wind, surface wind or the upper level winds. But in the previous mechanisms, they explain like when we have the negative NAO, the cold air move from Arctic into the European region and cold make the SST or surface temperature elongate a bit colder.
Amy?
Thanks, Abhi. I was wondering, your time series all stopped in 2013. So what's happened since then?
That's a very good question, because these are based on the CMIP6, and if you look at the CMIP6 simulation, the historical simulation stopped at 2015. But when I did the simulation, the index I got from the DCPP is yearly index, and that stopped at 2014. And when I did the experiment, because this doesn't go up to 2015, So what I did, somehow I didn't save the output for 2014. So that's the reason I just stopped it 2013. But also the other study, because this is the region like people look for the different time period. Like I found another paper that look at the trend from 1998 to 2013. So which went back just couple of years for two regions because to have the more data so we can do the significant like the test, we have more sample, and also to consistent with this like stop at 2013. But
In observations, did that cooling trend persist?
no, so if you go for a longer time period, no. If you increase the go a bit further up, you won't see that.
It levels off.
Yes, it's go away.
Does it start to warm?
I really don't know, but if you further go in time,
Yeah.
you won't see this cooling anymore. And if you see, it won't be significant.
I have one question and one kind of clarification.
Mhm.
So all along you're talking about December, January, February, right? So
Yes.
about the winter season has been cooler than you expect before.
Mhm.
Okay, so one question is there anything significant happening in other seasons?
I think, first of all, I look at the JJ and we haven't seen such cooling. But I think people do talk about a bit on fall season like SOM, but you won't see this strong cooling in that season. It's mostly in the DJF. But people do have like look at the Barrent and current impact on SOM, SAT as well. But the main look at the DJ because this cooling we are seeing in the winter season, you won't see in other season. So the answer is no, you won't see this strong cooling in other season.
Okay, that's interesting. So the other question I have is, do you think there's any role then for variability, extremes? Like, if NAO is related to shifting the jet stream, for example, is there also a tendency for the jet stream to be more or less stable in certain positions? This is something we think about in the ocean, so I'm just curious.
Honestly speaking, I don't know because I haven't looked those things. But it would be really interesting because is there any contribution these two streams or the NAO? But no, I really don't know because I haven't seen those things. But the PhD student I mentioned, the English she's looking on the extreme side. So she might look, because I look mostly in the mean state and she's going to look at the extreme. So maybe we'll see something like if there's an impact of these on extremes. But I don't know. Yeah, I'd say simply.
I just want to make sure I got the point right. Now, could you show again your very first model slide, the one that Amy clarified was prescribed, observed, total sea surface temperature?
So what are your questions? Say it again.
The slide with the first slide you showed with the model, prescribed, observed, sea surface temperature.
Oh, this one? No, this one.
It was 3 globes.
Oh, okay. So the where I said signal to no,
Yeah,
no,
okay.
maybe this one, or the observation, this one.
Yeah, it was what was on the right there. Oh, that was a single member. You handpicked a member.
So this is just a single member.
I see. You handpicked a member and agreed, but the ensemble does not. That was
Yes.
I see.
And the question is like here is like most of the time you will ask how I choose the first member.
One can find a member that can agree.
Yes.
But the forced part, yeah.
It doesn't, yes.
I get it. Thank you.
And this was luck, I would say. The first member is showing you because if you go to second one, you won't see the cooling at all.
Yeah.
But it makes sense why I choose the first one because when you start the simulation, you do the first simulation first, and then you go to second and third. So that's something is pointing in my favor, I would say.
Yeah, that's the whole history of the field. People did one simulation, published it in the 80s or something, and you do an ensemble and they lucked out or they anti-lucked out. Or
Yeah.
It's so silly. Yeah. Yeah.
Okay, I don't see further questions from here. Then, John, you can ask your question.
Yes, thank you very much. Enjoyed the talk. I have a question. The diagrams are so tiny, and I'm colorblind, so I'm flying doubly blind. I'm concerned about the permafrost in northern Siberia and also the underwater permafrost on the continental shelf. And it looks like that part is warm, if I understand this diagram correctly, and the cooling is further south. Is that correct?
So we, first of all, thank you. You said you enjoy my talk, so thank you very much. That's good to hear. But now just about your question. So which plot are you talking about? Are you talking about in the
Well, looking at the one that you've got up on the screen,
Okay.
it looks like the, that one right there in the middle.
Mhm.
It looks like the Eurasian cooling is further south, and it looks like the coast of Siberia is warmer. Is that correct? Go north.
Oh, you
The
mean
Arctic
like
Ocean.
so this area?
Yeah.
Okay. Yeah.
That's the most important place in the Earth in terms of methane release.
Yeah, but I would say it is showing it is warming, but actually it is not significant. So I don't know if we can trust that or not. And it is
Okay.
consistent in both. If you see the aerofoil as well as the hat crew, as well as in model we are not saying, but in both products it's showing it's not significant. So I don't know if we consider it is warming or not, because maybe just any.
Can you put up the NAOs?
Yeah.
The NAO regress,
Mhm.
just curious if that, yes.
And this is also.
NAO itself doesn't.
Yes, the annual does show a bit, like this is the region John was mentioning about, and I can say it does show a bit significant teleconnection. But this is just, sorry?
But it's cool.
It's going the other way around, and that's, yeah. And also this is just the interannual, so I don't remember what happened if you filter out the high frequency signal. John, have I answered your question or?
Yeah, I will come into the lab some future time, and I would really like to talk with you one-on-one where I can see the diagrams at large scale and have a more detailed discussion.
Yeah, thank you, and I'm
very
looking
much
forward to
enjoyed your
that.
talk.
Yeah, I'm looking forward to that.
Thank you so much.
You're welcome.
Okay, are there any further questions? I don't think so. Then thank you again for the nice presentation.
Thank you everyone for.
Thank you all for coming, and come again on Wednesday when Brian's new postdoc, Mathieu Raczynski, will talk about something. I forgot about what, but you will see it on Wednesday.